Okay, hello everyone. Welcome to our grand challenge session. I'm the session chair, Francis Yan, a networking researcher at Microsoft Research. And the other session chair, Zhixing Liu, my colleague, is also with me today. We're very excited about concluding our grand challenge on bandwidth estimation for real-time communications hosted at MMSIS 21. And first, I will quickly go over the challenge setup, and then we'll announce the challenge winners. Then they will receive cash awards sponsored by Microsoft and OpenNet Lab, and Zhixing will speak after me to introduce OpenNet Lab. Next, the challenge winners will present their solutions, and that'll be all on today's agenda. So let's get started. The preparation of our grand challenge actually started almost a year ago. And during the challenge, we received 6 valid submissions in total, including their algorithm implementations and paper drafts. And after reviewing all the papers, we decided to accept one of them. And today marks the end of our challenge, and we're about to release the evaluation results in a minute. However, before that, I'd like to say thank you to all the challenge participants. Thank you for your interest and your time and the effort you put in. We also appreciate the help from the General Chair, Ali, who helped guide us through the process. And finally, kudos to our organizing team at Microsoft. This is amazing teamwork. It goes without saying that real-time video applications are playing a critical role in our lives, and optimizing the quality of experience for QE for users is essential. And the bandwidth estimation, or BWE, algorithm works just like a TCP congestion control, but for RTC applications. And it basically adapts the video bit rate on the fly such that the sending rate is not exceeding the available network capacity. And it achieves so by computing a bandwidth estimate at each step based on some network stats. And then it will pass the estimate into the video codec to control the output bitrate. And this problem is actually a natural fit for data-driven approaches because we've seen that those classic handcrafted BWE algorithms often have trouble in the face of the heterogeneous real networks today. And in this session, our challenge winners will talk about how they formulated BWE as a learning problem. To simplify the challenge task for the contestants, we put some effort in providing a simple interface where the participants are only required to fill in a Python class. Once the Python class is implemented, our challenge framework will execute it in WebRTC as its bandwidth estimator. And in the meantime, since we hope to facilitate learning-based solutions, we also developed a simulation environment for training ML algorithms. And finally, each submission is evaluated in an automated fashion on a real testbed we built called OpenNet Lab, which Zhixing will talk about soon. And we performed a comprehensive evaluation, and in a nutshell, each submitted algorithm has been tested 405 times in total on OpenNet Lab, including 9 video scenarios over 3 types of networks with high, medium, and low bandwidth. And as for the score we used to evaluate schemes, roughly speaking, it constitutes an average weighted sum of scores for perceptual video quality, audio quality, and the network performance. Okay, so now we're very excited to officially announce the challenge winners. The winning team is from Nanjing University, and their solution has the highest score of 78.33. Congratulations to Tianren In and the team. Their algorithm is also the only scheme that has outperformed GCC, the default bandwidth estimator of WebRTC. So great job. And the running up team comes from the Communication University of China, and their solution achieved a score of 67.96. Congratulations to Bo Wang and the team. Their paper is also the only paper we have accepted. Although we have only selected 2 award winners, I'd like to congratulate all the other participating teams for completing this challenging task. They are from Peking University, New York University, National University of Singapore, and another team from Peking University. We spent a lot of time making the problem approachable by providing an easy-to-use framework. So we hope everyone enjoyed the challenge, had some interesting findings or insights that could be investigated further in the future. Yeah, that's the results. Next, Zhixun will talk about OpenNet Lab, after which we will have the winner and runner-up present their solutions. Okay, Zhixun, please take it away.
Yeah. Hello, everyone. This is Zhixiong from Microsoft Research. As you know, the challenge actually is a critical application of our OpenNet Lab platform. We do the evaluation on the top of it. So I'm going to introduce the platform briefly. In the networking community, actually, there is a huge gap between the research to the practical networking system. We have different behavior from diverse platforms, more and more user behaviors, and the complex new networking bottlenecks. To solve this, actually, we need heterogeneous devices, real applications, distributed nodes, and heterogeneous networks. This issue actually is hard to be solved by an individual. Our public infrastructure by our community is necessary. Next, please. Hence, we establish OpenNet Lab. This is the next-gen platform for open and practical networking research. This community provides the heterogeneous nodes, including the VM in the cloud and the PM in the campus, desktop, laptop, and smart devices. And also, we provide real applications. For example, the full-fledged WebRTC, the GEM for the WebRTC, Chrome, iPerf, and new applications. Also, the networks in the field, such as the campus network, cloud network, Wi-Fi, and 4G, 5G devices. Actually, the researchers can do the real network research with the networking and application data generated by the OpenNet Lab. Next, please. So far, actually, we have 34 nodes across Asia. If you want to join OpenNet Lab by using and contributing your nodes, please visit our website, opennetlab.org. Thank you.
Thanks, Zhixun. That concludes our opening, and we'll next have the first speaker, the runner-up and the accepted paper author, Bo Wang from Communication University of China. Bo Wang, it's your time.
Okay, can you hear me?
Yes.
Can I start now? Okay.
We cannot.
You cannot? You cannot? Sorry.
Example framework now. Okay. Hello.
1 second.
Okay. Okay. Hello everyone, my name is Daniel Ying. Today I'm presenting our paper, GEMINI, Example Framework for Bandwidth Estimation in Real-Time Communications. This was in collaboration with Hongyu Wu, Runyu He, Shushu Yi, and Dingwei Li in Nanjing University. My advisor is Jiaqi Zheng. Where it is a proposed solution, GEMINI, for the grand challenge on bandwidth estimation for real-time communications. The main goal of this challenge is to design and implement a bandwidth estimator on the receiver side of the provided RT system, AlphaRTC. It is a fork of Google's WebRTC code base. In this challenge, OpenNetLab provided AlphaRTC engine for reinforcement learning. At the same time, they also gave a limited number of network traces. The traces are measured in real environments such as 4G, 5G, and wired network environment. The model is scored mainly by the quality of audio and video network performance metrics. In fact, this evaluation system requires us to provide as smooth and fast bandwidth estimation as possible and reduce latency and packet loss. Real-time video applications have never played a more critical role in our lives as they enable us to live and work remotely while staying connected with the rest of the world. In fact, web real-time communications is widely used in areas such as enterprise communications, social applications, healthcare, education. It is used in everyday applications like Slack and Messenger. However, the rapid increase in the use of real-time video also poses a presented challenge for consistently delivering high quality of experience, such as high video and audio quality, low latency to all users. A pivotal algorithm to optimize the QoE for real-time video communications is bandwidth estimation. It runs on the endpoint of the real-time video occasion and aims at adapting the video bitrate dynamically to stay within the available network capacity. Bandwidth estimation is actually similar to congestion control problems. To solve such problems, the initial idea was to use rule-based algorithms. Google congestion control algorithm is one of these algorithms. In recent years, learning-based algorithms, particularly reinforcement learning-based algorithms, are developing rapidly. This algorithm trains the neural networks by learning the data generated by the real network sampling and some further adjust the neural network through online optimization such as PC family, passive, and so on. Some adopt hybrid learning-based methods, encrypting rule-based methods into their learning, such as ONIR. These algorithms have achieved certain results and become reference in our work. In our work, we consider that rule-based algorithms can help learning-based one. Aggregated RTP feedback packet information. These algorithms tend to elaborate state mechanisms and therefore have good convergence. Compared to the learning-based ones, the overhead of state calculation is much lower. However, they fail to achieve consistent high performance in complex and diverse network environment. Learning-based algorithms predict bandwidth based on neural networks trained by huge amounts of data. Deep neural networks tend to give it strong adaptability to network. However, training neural networks requires a lot of data and takes a lot of time and difficult to convert. Deep neural networks require matrix computation and bring high overhead. In fact, bandwidth prediction should not take up too much computing resources. At the same time, reinforcement learning is not so safe and is not very robust in untrained environment. It's not difficult to find that the shortcomings of the learning-based approach can be remedied by rule-based algorithms. Based on this idea, we propose our framework, GEMINI. The core idea of GEMINI is that we can take advantage of the DRL's excellent performance for a given environment while keeping the DRL stable inherited from GCC. In our framework, we mainly predict the bandwidth through two models, the DRL part and GCC part. We use a PPO algorithm for DRL training and refer to the WebRTC source code to implement the Python version of GCC algorithm. After receiving the RTP packet, we will predict the bandwidth through these two parts, and then through the overload detector, we can judge whether the current network environment is safe for DRL or not. If the environment is safe, we use the estimates from the DIR part as a result. Otherwise, we mix the results of the DIR and GCC parts. The exact ratio is determined by the trust window. We use a hybrid estimation as a result. In the DIR part of the GEMINI, the most important is the design of the state, action, and reward function. We choose receiving rate, packet loss rate, average RTT, latest prediction, and the difference between the current estimation, the current estimated bandwidth and the previous one as the state according to the information provided by the RTP packet. After receiving the state, the DIR model will calculate the action according to the internal neutral network and give it to the environment. We use a log-based function to normalize the actions. After the action is performed in the environment will compute a reward through the reward function. We hope that the design of the rewards will enable the model to predict low latency, low packet loss rate, high receiving rate, and less drastic changes. In the specific interface of this challenge, the bandwidth needs to predict every tenth of milliseconds. As a result, we use lightweight atom-critic neutral network. The top part is a atom network, and the bottom part is a critic network. In practical training, networks of this size can adapt to different network types. Pure DIR is not safe because of its black box neutral network. It may have unstable performance under the condition of inconsistent training environment and operational environment. Our solution is that we detect the overload signal or the unsafe signal and combine the DIR result with the GCC result. The core issue now becomes how to take advantage of the performance of the DIR as well as avoid the unstable performance. We use an overload detector, which is based on the delay gradients-based mechanism and dynamically updates the threshold. The design has similar implementations in both the standard version of GCC and ONIR. In addition, we use the trust window mechanism to adjust the proportion of DIR and GCC results. When the state is unsafe, we use a trust window to control the hybrid estimation. If the latest M signals are safe, the trust window will be increased by 1. Otherwise, it will be decreased by 1. By doing this, we can gradually use DIR data as the environment becomes safer. At the same time, when the environment is not safe, we can gradually shift the result toward GCC. We also use some tricks in training to improve the model's ability. OpenNetLab only gives us a limited number of network traces. These data are completely not enough for DIR model training. And we found some extreme data such as the zero rate that might be caused by unstable connections is not conducive to the convergency of the model. Therefore, we finally choose to generate data similar to the original data sample distribution. In the process of generation, we carried out data cleaning and removed the data that was too large or too small. In fact, the generated data trained models actually perform better than the models trained by real data when tested. We think this trick is also an important part of our implementation. And here are some details of how we implemented the GEMINI. In addition, we did some experiments to preliminarily verify the effect of GEMINI. GEMINI is actually a compromise between DIR and GCC. We reduce the latency relative to the DIR method and increase the speed relative to the GCC method. GEMINI can reduce the 95th percentile delay by 28% than DIR and under 4G networks with 700 kilobytes per second capacity. And here is a summary of our work. We plan to further improve the overload estimation mechanism in the future and combine some methods of packet processing with traditional algorithms during DIR operation. Thank you.
Okay, thanks, Tianren. Are there any questions? Yeah, we had a little change of plan. Tianren is from Nanjing University, and their solution is the winner. If there are not questions, we can go to the next talk from Bo. Yeah, I don't see any questions. Yep, Bo, please go ahead.
Can you see my screen now?
Yes.
Okay. Can I start now?
Yeah, sure.
Hello. Hello, everyone. I'm Bo from Communication University of China. I'll be presenting a hybrid receiver-side congestion control scheme for web real-time communication. This is a joint work with my advisor, Professor Yuan Zhang, and my schoolmates Sizhe Zipeng and Yu Hong. Firstly, I'm going to give an overview of a typical WebRTC transmitting session. For a WebRTC session, a media stream is first compressed and then packetized to an RTP packet stream at the sender side. At every decision-making interval, the receiver side controller estimates bandwidth based on a set of metrics measured from received RTP packets. Afterwards, the receiver sends the bandwidth estimate back to the sender via RTCP packets, allowing the sender side controller to decide the sending rate. In the grand challenge, the bandwidth estimate is fully decided by the receiver side controller, and the trace-based environment GEM simulated a WebRTC session, allowing us to train and test our model. Before talking about the model, let's focus on the challenge of designing a congestion control scheme for WebRTC. As shown in this figure, the objective of congestion control is to keep network links operating at the optimal point where in-flight data equals to BDP. But measuring bottleneck bandwidth and propagation delay abide by the uncertainty principle. Existing congestion control schemes for loss-based TCP are mainly based on filling and draining logics to address the problem. But WebRTC apps have stricter requirement on latency than loss-based TCP network scenarios, while still expect high-quality media delivery. It treats the excessively delayed packets as losses, which may bring severe damage to media quality. Therefore, most congestion control schemes designed for TCP are not suitable for WebRTC. To meet the real-time requirement, existing heuristic schemes estimate bandwidth based on a fixed and robust model that can hardly adapt to all network conditions. Learning-based schemes commonly employ deep neural network to generate bandwidth estimate. As a result, they have potentially better performance but are not robust enough. Recently, Abashlo and others have proposed an approach to combine heuristic congestion control schemes and deep reinforcement learning techniques, namely ORCA. It achieves consistent high performance in different TCP networks. Inspired by ORCA, we propose HRCC. We hope the idea of combining both worlds could be migrated to WebRTC. The framework includes two components. First, we implement a receiver-side version of GCC as a heuristic scheme. In our quickly to sudden bandwidth drop or high loss rate, but increases estimation slowly to sudden bandwidth rising, which means it tends to unrealized link capacity when the network suddenly got better or just highly fluctuate. Based on this feature, we implement an RL agent that periodically tunes the heuristic scheme's output estimate based on its observation on network. By combining two methods, HRCC aims to achieve the robustness of classic heuristic scheme and adaptability of learning-based scheme at the same time. The workflow of HRCC is quite simple. With received RTP packets, the heuristic scheme takes the related statistics of last decision-making intervals as inputs and generates bandwidth estimation and bandwidth usage state. Afterwards, the state generator takes states mentioned above to generate state input for the RL agent. At the end of every guide interval, the RL agent outputs a gain coefficient to tune bandwidth estimate. Now let's take a closer look at the control logic of HRCC. At the end of every decision-making interval, which is 200 milliseconds in this work, the heuristic scheme takes the statistics from arrived RTP packets and output a bandwidth estimate. We treat 4 decision-making intervals as a guide interval. The RL agent output a gain coefficient based on the observation of last 10 decision-making intervals at every end of guide interval. Now we focus on the key modules of HRCC. First, the heuristic CC scheme. It consists of 2 controllers. The loss-based controller calculates the packet loss rate based on the incoming RTP packets. In simple terms, a loss-based controller tunes down the bandwidth estimate when detecting higher packet loss rate and tunes up the bandwidth estimate in lower packet loss cases. And the delay-based controller calculates the delay gradient according to the received RTP packets and decide the trend of delay change and decide bandwidth estimate based on the trend line of delay change. Now we introduce the design of the RL agent. We adopt convolutional layers to extract the sequence features and Foley connection layers to encode the gain coefficient policy. For training algorithm, we choose PPO to train the agent. After every step of received RTP packets, the RL agent takes a 6-dimension vector ST. The state vector includes the measurements of the receiving rate, delay, packet loss rate, bandwidth predictions, the most current bandwidth estimation given by HRCC that caused overuse for the last 10 decision-making intervals, and the time so far since last overuse for the last 10 decision-making intervals. The more detailed information about the HRCC modules can be found in the paper. And now I'm going to give the simulation test results. To show the performance of HRCC, we train a fully RL-based bandwidth estimator with a structure similar to the RL agent of HRCC. We remove the state information given by the heuristic scheme from state input. It outputs a gain coefficient between 0.5 to 2 to tune the previous bandwidth estimate. We conduct the simulations under 100 network traces, each lasting 100 seconds. The average bandwidth of these traces ranges from 500 kilobit per second to 7 megabit per second, while 25 of them specifying 1% to 10% packet loss rate. As provided in the table, HRCC achieves the highest bandwidth utilization with similar delay and loss performance compared with the Foley heuristic scheme and outperforms the other two schemes on overall QoE. And now I'm going to give 3 specific test cases to take a glimpse of the performance of HRCC. These 2 figures show 2 cases of running simulations under different traces without random loss. As you can see in the left figure, in relatively stable conditions, the Foley RL-based scheme performs well enough. However, in the right figure, the Foley RL version lacks constraints on bandwidth estimate under the other traces that are completely different from the training data. The estimated bandwidth is totally off the trail and causes fatal fluctuations of queuing delays. Furthermore, we evaluate the performance of free schemes in bad network environments with random loss rates. As we can see, the Foley heuristic scheme cannot reach the available bandwidth with its loss-based mechanism, while the Foley RL-based scheme causes extremely high queuing delay, though achieves better bandwidth utilization. In this case, HRCC reaches the best compromise. By catching a glimpse of the 3 cases, we may see that HRCC realizes more robust performance than the Foley RL-based scheme and achieves higher bandwidth utilization than the Foley heuristic scheme. As a summary, HRCC outperforms both of its individual components on bandwidth utilization and overall QoE. In the following studies, first, there's related research shows that by interpreting deep learning-based models using decision tree method, the control logic behind the DNN could be dug out. In our case, we may find out why HRCC tuned in such way and perhaps improve it in a more precise way. Besides, overweight model could bring dramatic decision delay, and that's not tolerable for real-time communication. Transferring RL model into a decision tree may efficiently address the problem and make the model more applicable. Second, in actual application scenarios, there's non-negligible propagation delays for receiver-side estimation, sending back to the sender. So the feedback latency should be considered for deciding sender-side sending rate. We will work on that later. And with that, thanks for your attention.
Thanks, Bo, for the talk. And it's quite interesting that both solutions are using a hybrid approach, combining machine learning and classic heuristic approaches. So any questions for Bo? All right. I don't see any questions. So I'm hoping you guys can continue the work, and I hope you enjoyed the challenge. And congratulations again for winning the awards. So the top 2 places are both hybrid approaches, combining like RL and heuristic approaches. So it might be a sign of something. We got a question. So what would be the important research direction of RL RTC? Can you suggest some future directions? So yeah, as I said, so RL performance is quite unstable. It's a black box, and we all know that. So one direction of potentially improving the generalization or the robustness of RL algorithms could be just like this hybrid mode, right? We can leverage traditional approaches to optimize RL performance. Yeah. Are there other questions? So yeah, so making RL practical in real life is challenging. We need to improve the robustness, reliability, generalization, especially on those unseen networks, unseen environments during training. There's a lot of work to do. Okay, so that concludes our session. Zhixiong, would you like to say added a few words?
I think I think we can see the trend of the RL-based network, because maybe the 2 solutions are the sign of something, because it's very important for us to build a competence for RL-based networking.
Yeah, maybe they work better together.
Yeah, again, congrats to the 2 authors of the paper to get the awards.
So Francis, this is Ali. I have a question.
Hey, Ali.
Are you guys going to be back next year as well? Maybe with the same problem or a different problem, so that people actually can be a bit better prepared, this time. Obviously, we announced the challenges a bit late this year due to, all kinds of different reasons. But, it might be helpful if you guys are actually planning ahead. We might announce the challenge a bit in advance, giving more time to the participants, so that hopefully, it could be, quite an interesting another grand challenge.
Yeah, so if we have the plan of organizing another challenge, we'll definitely let you know as soon as possible. And it's been a pleasure working with you and working with MMSys. So I would recommend to other challenge organizers to do the challenge at MMSys. So yeah.
Thank you so much for
Thank you for the help.
Thank you.
Yeah, thank you.
Yeah, thank you so much, Ali, and everyone. Thank you.